Professor Muftah will introduce Professor Khattab.
Good afternoon, everyone. Professor Ahmed Khattab is an associate professor in the Electronics and Electrical Communication Engineering Department at Cairo University. He is also an adjunct associate professor in the American University in Cairo. He received his PhD in computer engineering from the Center of Advanced Computer Studies at the University of Louisiana at Lafayette, USA, in 2011. He received a Master of Electrical Engineering from Rice University in 2009. He also received his another MSc and his bachelor degrees from Electrical Engineering of Cairo University in 2004 and 2002, respectively. Dr. Khattab is the recipient of the Egypt State First Class Medallion of Excellence in 2020 and the Egypt State Encouragement Award of Engineering Science in 2017. He is IEEE senior member. He has a number of credits. If I go over them, they are really significant. His time will be quite thin at the end to present his presentation. However, I should say that Dr. Khattab has authored or co-authored 3 books, 3 book chapters, and 90 journal and conference publications, and a US patent. Before I do, and also he received several best paper and best thesis and best project awards from IEEE conferences. Dr. Ahmed Khattab, please, the floor is yours.
Thank you very much, Dr. Muftah, for this nice introduction, and it's my pleasure to meet you again. And thank you. I would like to thank the JAC-ECC team for having me over. And today I will be speaking about my experience in how the IoT can significantly change different fields of smart cities, such as smart farming and precision agriculture. So first, I will briefly introduce the concept and precision agriculture and how the Internet of Things technology can help advance such an important field. Then I would like to share with you 2 of my recent experiences with the use of IoT technology in the precision agriculture. More specifically, I will first talk about the project in which we developed an integrated monitoring system for forecasting the plant diseases for potato and tomato crops. Then I will talk about a recent collaboration with Spanish companies and Egyptian companies to develop a cloud-based integrated platform for monitoring best salinity and efficient irrigation in olive precision farming. Then I'll conclude my talk. So agriculture is one of the most ancient professions that man has ever worked. And up till now, agriculture plays a very important role in the economy of many countries worldwide, as you can see in this map, especially those developing countries in Africa, South Asia, and South America. Indeed, agriculture provides the main source of food, income, and employment to many people worldwide. For example, if we take Egypt as an example, and Egypt, as you know, is one of the main Middle Eastern and North African countries, the agriculture presents about 14 to 11% of the Egyptian GDP since 2009 till 2019. And according to FAO statistics, agriculture contributes to 20% of the Egyptian exports and up to 30% of the labor forces in Egypt, which means that about 1/3 of the Egyptian population work in agriculture-related businesses. Furthermore, if we take a look at the Middle East and North Africa in general, FAO statistics say that 50% of the food in this area is imported. Given the fact that the food prices is always increasing and the international market prices are going up and down depending on the situation, as we are seeing now in the COVID-19 crisis, the strategic importance of domestic agriculture becomes more clear and evident for the independence and the well-being of the citizens of different countries, especially in the third world countries. However, as we all know, agriculture faces several problems that can vary from the diseases and pests that affect the crops to the problems faced in the irrigation and the application of fertilizers. For instance, if we want to talk about the diseases and pests that affect the crops, they can result in a dramatic decrease in the productivity and the quality of the crops. For instance, in 2001, some of the potato diseases caused 60% of the crop to be lost. Likewise, an important pest that affect the olive plantation is the olive fruit fly, which can cause damage to up to 100% of the harvested fruit and up to 80% quality reduction in the table olive oil value. The old or the traditional practice in combating the disease and pests is to apply excessive fungicides and pesticides to counter these diseases and pests. However, such excessive application of fungicides and pests will definitely degrade the quality and the quantity of the crops. Furthermore, it will make the crops poisonous and not appropriate for human use or for exportation, which will have significant degradation of the agricultural process. Furthermore, the use of chemicals in the disease and pest control mechanisms will cause harm to the environment and will cause pollution to the environment, which is a huge risk or a huge downside that we want to avoid. So there is a need to be very careful in applying the pesticides and fungicides to combat the diseases and pests encountered in the agriculture fields. Likewise, another challenge is the irrigation and fertilization application. This is of very particular importance because of the need of the plant to do the different phases of growth varies according to different places, to different weather conditions, to different land types. So we need to be very careful in applying the water and the fertilizers. However, the traditional way also was to use massive or to flood the entire field with water, as the case here in Egypt, which is totally non-appropriate. And there are many other factors that affect the application of irrigation and fertilization, specific to certain places, such as Egypt, which has 25% of its agricultural land is reclaimed desert plots, which lacks nutrition, it lacks the availability of water sources. The soil in the Sahara Desert plots lack nutrition at all and results in very low yields. Furthermore, the building of the dam in Ethiopia might result in water shortage in Egypt. Indeed, according to FAO, Egypt is estimated to be among the top 35% water deficient countries in the world. So again, we need to be very careful in the use of water and fertilization in order to combat all these negative sides in the irrigation and fertilization application, as well as the case in the disease handling. The solution to all these problems is the term precision agriculture. Precision agriculture refers to a mechanism in which the right set of inputs, for example, water, fertilizer, fungicides, are applied at the right time and place whenever needed by the plant, which considers the microclimate conditions to control the application of such resources. Indeed, the US formally recognized the precision agriculture as the main type of agriculture in 1997 by the US Congress, and since then, precision agriculture has been adopted in many countries worldwide because of the many advantages it brings to the table. For instance, it increases the crop quality and quantity, because here we are applying or we are treating each plant individually and applying the right set of resources whenever needed. No excessive water, no excessive fertilizers. So it economizes the needed resources. Furthermore, it provides a better estimate of the real crop needs and accordingly adapt to the needs of the plant. And it provides the farmer with better prediction of the crop yield and allows the farmer to set up a detailed history of a given field practices and the crop output in order to help him plan and time manage and decide what to be done for the next cycles of agriculture. More importantly, it protects the environment because of it doesn't allow the excessive use of chemicals that cause pollution to the environment. However, precision agriculture faces different challenges, such as the need for maintaining the system sustainability given the harsh condition or the variable condition in the field in which the precision agriculture system operates. Also, there is a need to achieve automated and accurate yet low-cost measurements of the required parameters of the environment without any human intervention in order to achieve accurate sampling of the data. Collecting these measurements and processing them should be done in a timely manner in order to take the most appropriate actions in the appropriate time. Furthermore, doing all this should be done at very low maintenance requirements and very low cost. And in countries like the developing countries, there's a need to secure and guarantee theft-proof environment for placing the equipment used for precision agriculture. And here comes the importance of the IoT and how to make the precision agriculture IoTified in order to address all these challenges of providing automated yet accurate and advanced processing of the information to be collected. In the next few slides, I will briefly introduce the Internet of Things technology and how it provides an excellent solution for smart precision agriculture. The Internet of Things paradigm refers to a network in which physical objects, which can be anything, it can be our cars, our appliances, any devices or any building that can be uniquely identified with a virtual representation in an internet-like structure such that it can be connected to the network. And these devices are embedded with electronic hardware and software and sensors with network connectivity in order to communicate with each other and communicate with the internet. The term Internet of Things was first proposed by Kevin Ashton in 1999. Typically, IoT systems consider the shown layered architecture, which is composed of 4 layers. The lowermost layer is the sense and identification layer, which corresponds to the physical layer, which is responsible for gathering the information from the environment or doing some action to the environment. And this layer is basically the physical layer, which has the sensors. And now we have thousands or millions of sensors that can sense practically anything, and actuators that takes action in the environment. The second layer is the network construction layer, which is responsible for transmitting the collected information through any wired or wireless communication technology. The collected information is transformed to the third layer, which is the management layer, which is responsible for processing the gathered information and storing them in data centers and applying smart decision, artificial intelligence, and securing the data or do any information processing techniques needed over the collected data. And finally, the last layer is the application layer, which provides an interface to the humans through any API or any data visualization technique. As we can see that the 3 main enablers of the IoT technology is the device miniaturization. And as you can see, the size of the computing devices went down from the size of the mainframe in the 70s or 60s. And now we have microprocessors that can be as small as they can fit inside a medication bill or so. Another key enabler is the cloud computing and the advances it's witnessing right now, and how we can now store data, process data, and have different applications that connect to this cloud. And furthermore, the artificial intelligence and machine learning and other analytical approach that helps us to analyze the collected data and really find trends and make them useful. Because it's very important to really make use of the collected data, not just collect pure data. Consequently, the IoT technology has found its way to almost every aspect of our modern life in smart cities, in buildings, in streets, in factories, in the sea, on the ground, and in smart farms, as we are discussing in this talk. So basically, sensors are everywhere now. And this can be further demonstrated by the shown figure, which shows in the blue line, the population of humans have increased from 6.3 to 7.8 billion human beings from 2003 to 2020, which is about 1 billion human increase. On the other hand, the number of devices that are connected to the internet has increased from almost 1 billion to 50 billion smart objects connected to the internet. And the communication or the wireless technology have totally changed from just having each person have just one mobile phone that connects him to the network to communicate with other humans, to now we have almost 6.9 devices per person to allow him to interact with the environment. We have smart doors, smart cars, smart shoes, smart watches, smart Google smart glasses, and so on and so forth. There are many other numbers that give the change in the wireless technology. For example, Huawei forecasts that the number of connected devices by 2025 will be 100 billion IoT devices. McKinsey Global Institute suggests that the financial impact of the IoT on the global economy might reach 11.1 trillion by 2025. There are many other different numbers that shows the importance and the significance, growth, and influence of the IoT. I cannot say that there is one that is very accurate, but they can give us a big picture of the importance of the IoT in our lives. That said, now we are ready to hear about our experiences with IoT in precision agriculture and smart farming. The first project I would like to talk about is the integrated monitoring system for plant disease forecast, which we have developed for forecasting the diseases facing potato and tomato crops. This project was done in collaboration with the Agricultural Research Center in Egypt and was funded by the Science and Technology Development Fund, STDF, here in Egypt. The main goal of this project was to develop a system, the hardware and the software, which predicts the outbreak of, or the condition that will lead to the outbreak of the diseases, and accordingly advise the farmer with the best action to be taken in order to combat such diseases. And this is the system function overview, which is composed of three main parts. The first part is the hardware, which is composed of the sensors, both underground and above ground, which collects all the attributes that were recommended by our agriculture experts. On the other hand, the agriculture experts did a lot of in-field and lab experiments in order to develop the mathematical models that predicts the outbreak of the different diseases that we considered in our research. The sensors collect the data and wirelessly communicate them to our research center in order to process them and take the decision. And in order to do so, we have implemented what is known as an expert system. An expert system makes the control and corrective actions, initiate the early warnings, and produce maps and visualize the events in order for the farmer to be able to monitor what's going and help intervene if needed. Furthermore, the collected data was evaluated based on the initial models developed by our agriculture experts. However, we were using AI and machine learning techniques in order to further improve the models of the diseases. For the first part, in which we were aiming at implementing or developing an agriculture weather station, which collect the required information, such as the wind speed and direction, air temperature and humidity, solar radiation, leaf wetness, rain meter, and the soil water content or the temperature, which were buried underneath the ground. We have specified the needed sensors with the required accuracy and resolution recommended by the agriculture experts. And we have built our agro-weather station based on an Arduino Mega, which was powered using a solar panel and rechargeable battery as shown in this schematic. The station collects the data and sent an SMS message to the remote center, which contains the information as shown is in this slide. The expert system software design is composed of three main modules. The first module was responsible for logging the collected data that was sent by the SMS messages. The other part is the AI module, which is based on the ground layered architecture for integrated reasoning, the GLAIR platform, which learns the trends in the data and come up with decision what to be done and when this action to be done, which is a reasoning platform. Finally, we developed an application interface that allow the end user to see the statistics of the collected data and the trends and have histograms of the information. And this is an example of a disease model, which is a set of conditions upon which a decision whether or not to apply a specific treatment or not. This is just a simple model just for illustration. And here is some snapshots of the application interface that we have developed, which allows the farmer to define new weather stations and define the number of events and which events, and define the different ranges for the different events and when they are considered to be harmful or not. And this is example of the reported data. And as we have 6 of these agro-weather stations deployed in different governorate around Egypt. Actually, we have in 6 governorate, and these are real measurements by our base station. And the outcome of this research has been published in Computers and Electronics in Agriculture journal. The next project that I would like to talk about is a collaboration with the Spanish government in the Egyptian-Spanish IT Innovation Program, ICETIP, which was funded here in Egypt by the IT Industry Development Agency, or ITIDA, and in Spain it was funded by the CDTI, which is equivalent to ITIDA in Egypt. And the collaboration or the team was composed of Cairo University, Smartec, which is a leading IoT company here in Egypt, and Ceresco, which is a multinational company that is based in Spain, which is called Ceresco. So the goal of this project was to develop a cloud-based integrated platform for monitoring pests, salinity, and efficient irrigation for olive precision farming. The motivation of this project was the fact that Egypt and Spain are 2 of the world's leading table olive producers, with Egypt producing 18% of the world production. On the other hand, Spain is the largest olive oil producer in the world, with more than 45% of the total world production. Spain is the first country in the planted area. Spain had in 2017 2.6 million hectares devoted for the cultivation of olives. Therefore, exploiting the ICT technology in such a growing sector represents an excellent opportunity to boost agriculture productivity in both countries. However, the olive farming faces many challenges. We identified the most important or the most severe problems that face the olive farming, which can be summarized in the next few slides. The first and the most important disease that affects the olive trees is called the verticillium wilt. Verticillium wilt is a soil-borne fungi which invades the root system of the olive trees when the temperature is cool. So it starts in winter and ends in spring. It suffocates the trees, as shown in this figure, by preventing the water from reaching the xylem, which causes the tree to suffocate. So again, the progressive invasion usually occurs in the late winter through spring, and when the temperature increases again above 30 degrees, the fungus is inactivated. However, it becomes active again when the weather cools down. However, there is no cure whatsoever for the verticillium infected trees, even though some people try to prune the affected branches. However, verticillium wilt is a root related fungus which cannot be treated by just pruning some of the branches. So this is one of the goals of the project, is to early predict the occurrence or the condition that will lead to the outbreak of the verticillium wilt disease. Another important problem that we are targeting in this project is the fact that the accumulation of the salt in the water used for irrigation, especially in countries like Egypt, as we use saline water for irrigating the olive trees in the Sahara area and in Sinai and in Matruh. So the accumulation of the salt will cause some surface that is impermeable, and the roots again suffocate and stop exploring the soil for nutrition, and hence the trees will die. The accumulation of salts is affected by many factors, as shown in this figure. More specifically, the climate conditions, the soil type, the irrigation water quality, especially when saline water is used, and also the type of the tree, because there are different types of olive trees worldwide that act differently with to the irrigation water. So we want to develop some recommendations on how to use saline water for irrigating the olive trees based on the census information. The third and the last problem that we are tackling is the olive fruit fly, which is an ancient pest that have been identified in the Mediterranean region since the 3rd century BC, as was written in the Greek Roman writings. The olive fruit fly presents a major threat on the olive plantation, and it may cause up to 100% of the harvested fruit to be damaged, and it can cause losses to up to 80% of the olive value because of it lowering the quantity and the quality of the olive oil. The population of the olive fruit fly depends on several climatic conditions, such as the humidity. It flourishes in humid environments, and also when the temperature goes between 20 degrees Celsius and 30 degrees Celsius, it presents an ideal environment for the olive fruit fly to flourish. So now we can state our objectives is to set a step forward in the Egyptian and Spanish strategy of using technology to improve the agricultural practices by monitoring the environment factors affecting the olive plantation, and detect and count the major pests such as olive fruit fly, and monitor the irrigation water and soil salinity characteristics, and present a profile or advice recommendation on how to use saline water for irrigating different types of trees in different land, in different types of lands. In order to achieve these objectives, we are planning to have, or are working on having, a hardware platform that is composed of the monitoring station, such as the one developed in the first project, as well as having a pheromone trap that attracts the olive fruit fly in order to count them and apply the appropriate countermeasure accordingly. Associated with this hardware, we are working on developing a decision support system, or a DSS, that serves as the single point of access to all the collected information, as well as a platform for implementing our decision-making processes and machine learning and artificial intelligence decision-making processes. Before we implement the hardware, we planned the network architecture as shown in this slide. We are having some remote sensor nodes to be deployed near to each tree that we are monitoring closely, in order, for example, to assess the irrigation water effect on the plantation. We are also having the pheromone traps that attracts and counts the olive fruit fly. These remote sensor nodes and pheromone traps will collect the needed information and relay them to the main node, which is acting as a gateway that connects the system to the network server, which in turn connect and relay the information to the cloud platform, where the AI and machine learning and other APIs exist. Hence, the users can connect to any internet-enabled device to this cloud platform in order to access the data or issue any commands. For communication between the remote sensor nodes, pheromone traps, and the main gateway, we chose the LoRa communication paradigm. The LoRa communication, or the LoRa WAN features, are very attractive because using a single gateway or just one base station can cover entire cities or hundreds of square kilometers. Indeed, the coverage range of the LoRa is 9 miles or 15 kilometers approximately. It provides appropriate data rate of 50 kilobits per second, but most importantly, the lifetime of the LoRa technology is about 10 years. Hence, it alleviates the need for harvesting the energy frequently. Consulting with our agriculture expert, we have identified the needed weather attributes that need to be measured by our weather station, and the ranges and accuracies needed for them. And similarly for the soil sensors, and as you see, we are deploying sensors underneath the ground at different levels in order to have a complete picture of the salt accumulation underneath the ground. Likewise, we identified the LoRa technology transceivers and the camera board that are needed for best performance of our system. And accordingly, we have implemented the different nodes and the gateways as shown in these few slides. And now we are done with this phase. And currently, we are deploying the nodes in several test beds, both in Egypt and in Spain. For instance, in Egypt, we have partnered with a groove near the Suez Canal, as shown in this figure. This groove has different types of soils, both deep sandy soil, sandy loam soil, and shallow clay soil. The irrigation there is done through a highly saline water, there are more than 14,000 trees of multiple olive varieties, both Egyptian olive, Spanish olive, Italian olive, with different trees, ages, and different characteristics. Likewise, our Spanish partners have identified several farms according to the fact that they have new plantations, and these plantations have signs of verticillium wilt that we are targeting to predict. For the best monitoring, for the olive fruit fly monitoring, 3 different farms have been identified in Sevilla, Cordoba, and Jaén. Also, we have identified a farm in Valencia for managing and monitoring the irrigation water salinity. In total, the Spanish test bed is composed of 5,678 hectares. On the software side of the platform, we have developed a cloud-based platform which is responsible for recording the acquired data by the soil sensors, the environmental sensors, as well as the pheromone traps. The platform processes this collected information using artificial intelligence techniques in a predictive model of pests, diseases, and irrigation optimization. And I will briefly talk about one of these models for pest detection and counting. And finally, the platform provides a very professional application layer web interface in order to allow the users to access the information. What we have done in order to count the olive fruit fly is what is known as integrated pest management system, which is an efficient way to reduce the population of the harmful pests. Basically, as shown in this figure, traps are deployed across the field, and these traps are filled with some substance which are called the pheromone, which attracts some species of flies. And here we are using olive fruit fly attractive pheromone trap, and they will just attract the flies, and once they get in, they are stuck. So we take pictures and develop a decision support system that counts the number of captured pests and accordingly advise the appropriate action to be taken. And actually here we are partnering with a company that does biological countermeasures, not just using pesticides as the traditional way. So the traditional way for olive fruit fly counting was manual, in which the farmers go to each one of these traps and manually count the number of pests, and accordingly they decide what to be done. However, such a manual counting technique is labor intensive and error-prone because it's dependent on the human in the loop, expensive, and very, very slow. Later on, there was a semi-automatic approach in which digital images of the sticky sheets can be captured and analyzed by the human experts in order to recognize and count the pests, which is definitely better than the manual counting. However, it still has man in the loop, and therefore it will suffer from the same problem suffered by the manual counting. Our approach, on the other hand, is totally automatic. We will add cameras that capture the trap photo and send it wirelessly to the cloud platform. And we are using state-of-the-art machine and deep learning techniques in order to detect and count number of pests. And this is totally remove the human from the loop in order to achieve a completely automated real-time pest monitoring system. And actually, we did a detailed survey of the different olive fruit fly counting, and we have a book chapter that was recently accepted for publication in the Deep Learning for Sustainable Agriculture by Elsevier. Accordingly, we have designed a new approach which detects and counts the olive fruit flies from the captured images with high accuracy, and our goal is to have its size as small as possible in order to fit in the embedded system, not only in the cloud. And also, we want, or we have trained our system using the DIRT data set available for olive fruit flies. And this is an overview of the developed framework, which has 3 main components: image preprocessing, data augmentation, and then the you only look once, or the YOLO platform for counting and detecting the occurrence of the olive fruit fly. Briefly, the yellow mean color normalization step is to normalize the intensity or the light intensity inside the trap, as is shown in these pictures. Then we increase the size of the training data by different augmentation techniques. And then we have modified the YOLO platform in order to achieve the highest possible accuracy. And our initial results have shown that our framework significantly improved the precision, the recall, the map, the F1 score compared to the original YOLO platform. So to conclude my talk, the use of IoT in smart farming and precision agriculture is a step forward in the strategy of using the ICT technology to improve the agricultural practices. It increases the farming production quality and quantity and reduces the environmental pollution. It improves the competitiveness of the farmers and facilitates the adoption of technology and technological innovations. Furthermore, it contributes to achieve sustainable agricultural development, which definitely will help different countries worldwide. Thank you, and I will be glad to hear any questions.
Thank you. I have here a question from Hani Ragai,
Sure.
saying a few days ago when we heard about farmers' capability to use their mobiles for PA.
Yes.
How credible is this?
Professor Muftah, can I ask a question at the end? I am Amin Shukri from eJust.
Okay, thank you.
Thank you.
Okay.
Yeah.
Actually, we had really a big problem in applying our concepts when we were working on the potato and tomato. Indeed, we need to have some incentive for the farmer to adopt this technology. For instance, we were sending them text messages. If you apply this fungicide or if you do this action, you will receive 50 Egyptian pounds or so. So there definitely initially, we need to have some incentives in order to make the simple farmers adopt such technologies. But once they appreciate and they understand the gains that we receive, they will automatically go for this option, and they will forget about the traditional ways of farming.
Yeah, thank you very much.
You're welcome.
Dr. Amin Shukri, please go ahead with your question.
Yes, thank you, Professor Muftah. I am pleased to see you with us today and hope to see you at eJust premises in a very near future. Also, I thank Professor Khattab for this nice presentation. My question is about what, intelligent reasoning system he has used, because in his presentation, of course, he talked about several models, but sometimes he talked about an expert system, about an intelligent agent, machine learning, deep learning. So my question, if he can give us more precisions about what reasoning mechanism he is using, or a hybrid of several things. I hope that he understands my question.
Sure, definitely. Actually, it's application dependent. For instance, in order to forecast the evolution of weather, in order to predict the weather condition that would affect something like the growth or the development cycle of the olive fruit fly, we are using time series analysis, using long short-term memory, and you're using other techniques that predicts the time series of the growth or the evolution of the temperature. On the other hand, we are using deep learning technique, which is called YOLO, you only look once, which is like deep learning. It's a convolutional neural network which predicts or it divides, as shown here in this picture, it divides the picture and take decisions and do some classification in order to identify the best. On the other hand, on the first platform, one of our collaborators has developed something that is called the GLAIR, the grounded layered architecture with integrated reasoning, which was used to refine the models that were initially developed by the agriculture team.
Okay.
So again, it's application dependent. There is no one answer. There is no hybrid. Again, depending on the application, we can have a specific technique to address or to identify the needed data, or to analyze the available data.
Thank you very much, Professor Khattab. Thank you.
You're welcome. You're welcome.
Thank you very much. A final question from Dr. Hana Shaker. What are the most common types of attacks in this area of research, and what are the most common anti-spoofing methods to mitigate these attacks?
This is a very good question. And actually, we have not considered this dimension yet. We have more fears of people stealing the actual hardware. So we are just building fences around the sensors in order for them to not be stolen. We haven't considered this very important research, of course, securing the data, but I don't have an answer for this question. We haven't considered it yet.
Okay.
We have some security features for the cloud system in order to prevent our platform, but these are built in the used cloud system. So, but research-wise, we have not developed anything yet.
Okay. Thank you. I have also here, I would like to ask Dr. Abu Zahad to ask a question, please. Go ahead.
Okay, thank you very much, Professor Muftah, for helping JAC-ECC in chairing the session. Thank you, Professor Masoud, and I am glad to see Dr. Ahmed Khattab.
My pleasure, Dr. Muhammad, to see you, and thank you for the invitation.
In fact, I am not following the lecture from the beginning, but I have a little question about early detection of pests. The system can detect early problems in agriculture farms.
Yes, yes. I didn't elaborate more, but I will tell you exactly what happens. We have developed predictive models that predict the evolution of the temperature, for example, for the next year. And accordingly, there's something that's called the day degree, which computes the temperature units that affect the growth of the disease. And accordingly, we can forecast or foresee when the disease or the pest will have an outbreak, or it will develop, or the larva or the egg of the fly will hatch. And accordingly, we can take the appropriate action. For example, we can advise some people to shake the trees to make the eggs go under the ground, and so on and so forth. So this is how we are tackling the forecasting problem.
Okay. Is there a reason to adopt your system in Spanish farms, not in Egyptian farms?
They are facing different, during the negotiation phase, they were facing a lot of problem with the verticillium cell. The verticillium wilt, it's not severe in Egypt, but they are suffering from it a lot. However, they are not using saline water, they are using normal water. So they don't have the salinity problem. But here in Egypt, we have the salinity problem. So in the negotiation phase, we reached like a middle ground or a common ground in which we address both the Egyptian and the Spanish problems encountered in the olive plantation.
Okay, thank you very much. Thank you, Professor.
Thank you, Dr. Muhammad, and thank you very much for having me over.
Thank you very much. And I would like to end the session at this moment. And I would like to thank very much Dr. Ahmed Khattab. And it's a pleasure indeed to meet you again.
It's always my pleasure, Dr. Hassan. It's always my pleasure. Thank you very much.
So if Professor Masoud has a question.
Thank you very much.
Sorry. Yes.
Sure,
Yes,
Dr. Masoud.
Dr. Masoud, please go ahead.
I just have one question regarding the sensors that you presented you put in the ground to make the detection. Are these ready-made sensors, or you developed it?
No. Actually, we thought to develop them because they are measuring the conductivity of the water. We thought we are having Dr. Surak Habib, Professor Surak Habib, which is very well known, and we thought to develop them locally. But at the end, we decided to import them. But okay. Yes, you are right. They can be easily manufactured locally.
Okay. Thank you very much. Thank you for the great talk. Thank you.
You are welcome. Thank you very much.
Thank you, Dr. Masoud. Is there any first question at the end? Anyone would like to ask questions? All right. Okay.
Thank you so much, Professor Ahmed Khattab, for your interesting talk. And also thank you, Professor Muftah, for chairing the session, and Professor Masoud Al-Ghunaimi. Thank you so much.
Thank you.
Thank you.
Okay, thank you all for this is the end of our session. I would like again to thank our chair and our speaker.